let's start what we were discussing in the last class, and we were talking about this sub-assemblage. We had assumed points of contact vector in the mid height of the columns, and similarly at the mid span of the beams, let us say the effective rigidity of beam is EIB and that of the column is EIC. Okay, and we are trying to plot the load versus displacement curve for this sub-assemblage. Okay, load applied is Q and then it is deformed, and for plotting the deformed shape, let's consider this as equivalent to, okay, so we had also calculated this reaction, and how much was that reaction? DH by QH. So you can see both of these are equal, and we have not considered any axial force. So the axial force at this support, the reaction at this support will be 0. Okay. So in that case, when these two reactions are equal and opposite, and in which case these reactions will be equal? When the two beam spans are equal. Okay. So in that case, we can also consider this as because the horizontal reaction Q is also acting here. So can I consider this as same as this? Here, how the deformation was occurring? We have plotted the deformed shape. This was our deformed shape. And the displacement is, and we have to plot Q versus delta. Now here, how the deformation will occur? Because here we have provided a hinge support, so it cannot move horizontally, but rotation can occur. And then these columns are going to deform like this. What is the displacement here? Delta by 2 occurring here, and delta by 2 occurring here. Total displacement is delta. This delta is same as this delta. You agree? Now this delta, which you see here, and you can see more clearly here, okay, it is having two components. One because of the bending of the beam, and another one because of the bending of the column. So even if I assume the column to be rigid, then the deformed shape would have been, if the column was rigid, then the deformed shape would have been like this. You agree? So this displacement, which is occurring due to rotation of beam only, because this joint has rotated. Okay? Column has not deformed. Even if column remains straight, even then this displacement is occurring. That displacement we will call delta B. The displacement due to bending of beam And then the column itself is bending. The column below the story is also bending, the column above the story is also bending. Okay, so this additional displacement which is coming, that is delta C by 2 here and delta C by 2 here, and the total displacement delta is delta B plus delta C.
Sir,
Yes.
how delta by 2?
Because half is occurring here, half is occurring here, and this is half occurring with respect to this point. Half is occurring here, half is occurring here. Okay, let me plot again. Suppose this is our beam and I take column as rigid. Column is rigid. And I apply a force Q here. And I have to apply equal and opposite force Q here. Then what will happen? This column is going to rotate. Isn't it? This column will rotate and the beam has to remain perpendicular to it. The beam will bend like this. So because of the bending of the beam, the displacement is occurring. So you can see that the total displacement, if this is between the bottom point and the top point, it is delta. So half of this is occurring on this side and half of this is occurring on the other side. Now same thing if I consider as bottom hinge, then how the deformation will look like? In this case what will happen? In this case my column is going to bend, not bend, rotate. Because this is rigid, so it will not bend, but it will rotate. Okay. And then my beams, which remain perpendicular to it, will deform like this. So if this rotation of the beam is theta, you can see that this angle is also theta. So what is happening? This total is delta, and here it is delta by 2. Okay. In this case, we are measuring from here. So when you will measure from here, delta by 2 will be on this side, delta by 2 will be on the bottom side.
Sir,
Yes.
the displacement due to the translation.
Yes. Okay, just a minute. Let me call it delta B because it is occurring because of the bending of beam. So column has not yet bended. So let me call it delta B. Okay, tell me, what's your question?
The displacement due to the translation of this beam along horizontal direction will be equal to that column displacement.
Right. So this delta B here, let me call this also as theta B. So delta B is theta B into H.
It will be happen when both the points having same Q.
Both the points have?
Same Q.
Yes.
Here and Q are the same.
Right.
That's it will be happen. If it is different, that the data is not same.
We will come to that case later. At the moment we are assuming that there is floor load acting at the top. Let us say there is no floor load acting at the floor. So the force which is acting at the mid height of one story is same as, so the case which we are considering here is this case. let's apply a force Q here. Then what will happen? This force and this force is equal. Suppose I apply a force here also, then there is not equal. We can consider that case also, but that we will consider later.
And the second one is second order.
Yes.
You have considered that the column between two hinges are rigid. Rigid actually.
At the moment.
At this
But that is not end of the story. I am going to consider flexibility also. Okay, it is not that I will finally keep the column rigid. Just to divide into two parts, delta B and delta C, I am considering two cases. First, I will consider the column to be rigid. Just to tell you that the total deformation consists of two components, one because of the bending of the beam and another one because of the bending of the column. Okay, that's why I have taken it. So I will first take this case where the column is rigid. I will consider the second case where the beam is rigid. Let's consider the other case when the beam is rigid. And column is flexible and same forces the column is subjected to. So what will happen? Due to bending of column alone, you will have delta C by 2 this side and delta C by 2 this side. Okay, and delta S, delta B plus delta C. Both the cases you will superimpose. So this case and this case you will add. So first case you are considering the effect of flexibility of the beam or bending of beam. The second case you are considering the effect of bending of column. Let's calculate those one by one. Can you tell me how much is delta B, or let us say delta B by 2? So that is nothing but can you calculate theta B? How to calculate theta B? You can calculate this deformation. Okay. And then divided by length, you will get this. This reaction, you know, how much is this reaction? So, due to this QH by L, how much will be this delta? Let me call it something else, delta dash, because delta we have used for a different purpose. So, this delta dash is how much? It is like a cantilever, isn't it? It is as if this is a cantilever and you are applying this force to bring it to the horizontal. So, this force is just adequate to bring it to the horizontal position.
Sir,
So, how much is this displacement? PHP over 3I.
But sir, here we can't consider that as cantilever. Reflected shape is not like cantilever.
It is like cantilever. How will it be formed? So, same thing I have brought it here.
Yes.
So, it is like a cantilever and this displacement is delta dash.
Let's say if I am taking structure like this is here roller hinge, and I am applying load like this. Deflected should will go like this. This will go down. This will go up. Here this is theta.
Right.
If I am to find the deflection at here, then this delta will be this theta b into L plus PL cube upon 3A.
Right.
Here same this is happening here also.
Yes. But from where we are calculating this displacement? We are calculating this displacement from already rotated position. See, I am calculating with respect to tangent. There you are not calculating with respect to tangent. You are calculating with respect to the horizontal. Here I am calculating with respect to the tangent.
No, but displacement you have taken delta is from horizontal.
No, I have taken from this tangent to this point, not from here to here. Okay, I will explain in your case itself, let other also understand. So, what he is thinking is that let us say we have a beam overhand beam and I am applying a load. And second case is that I have this cantilever and I am applying this. So in this case, it is going to deform like this. Let us say this is delta 1. In this case, this is going to deform like this. This is delta 2. Okay. What he means to say is that delta 1 and delta 2 will not be same. You will like it? Will delta 1 and delta 2 be same?
No.
No. Okay. Why not same? Because here is a rotation also happening. Let me slightly exaggerate this deformed shape. Then it will be even more clear. Okay. So this delta 1 and delta 2 will not be same. And what appears here that I am considering, because in my case this is also rotating, this case is also similar. Only thing is that here rotation is occurring this way, here it is occurring on the other direction. But this support is also rotating. So in this case, one component is because of the bending of this portion of the beam. Another component is because of the rotation. So you can separate the two components. You can draw a tangent from here, and this displacement with respect to the tangent will be same as delta.
That will be same.
So if you are taking your displacement with respect to the tangent here, then you can treat it as a cantilever. But the support of the cantilever has to be normal to the tangent at this point. Okay. So this condition we are using here. This is the tangent. Okay. And from tangent I am calculating the deformation. So this deformation will be same as that of the cantilever. Okay. So can you calculate delta dash then? So this delta dash is not from the original position, but the tangent from the tangent at the support which has rotated. Otherwise this displacement from the original condition would have been 0. So how much is delta dash? QH by L into okay, and theta B is delta dash by H by 2. So how much is theta B? Can you simplify and tell me?
Theta B at the because of rigidity of the column is equal to the theta B for that beam is equal if EIB equals to EIC.
Sorry, it is equal to
EIB equals to EIC.
EIB equals to EIB.
So it's that EIB and EIC.
Both are same. Why? We have not bent column at all. Column is having infinite area. So why you need that condition? That EIB has to be equal to EIC.
Because of that rigidity means theta B, how we can say that it will be same.
Because of the compatibility. The angle here
90 degree.
90 degree. So this angle is 90 degree. When it is rotating, then this angle has to be 90 degree. So we are saying it from compatibility. Any other question? Yes, Anil?
Delta we calculated yesterday. When we consider the column has the pin at the lower end and has a rigid column, that is delta V. Now, when we converted it into a equivalent structure with QLP towards right and towards left of the column, that the displacement of the that delta, that should be delta V by 2.
Yes, we have calculated delta V by 2 only. Yes. Delta V by 2 will be h by 2, delta V will be theta V into h. Yesterday we have done delta V as theta V into h. Today we are saying delta V by 2 as theta into h. Well, both are the same thing.
Previous slide you have not.
Which previous slide?
Delta V equals delta C by 2.
No, delta will be delta V plus delta C by 2 because half is occurring this side, half is occurring this side. Total will be double. So earlier I was considering full. Today I am considering half.
So at one end, the total displacement will be delta V by 2 plus delta C by 2.
Right. And total displacement will be delta V by 2 plus delta C by 2 here plus delta V by 2 plus delta C by 2 at the other end. So total will be still delta V plus delta C. So how much is theta V? Yes, not h by 2, this will be L by 2, you are right. Okay, so this distance is L by 2, not h by 2. Yes, so how much is theta V? QH L or L square? Check it. L by 2 is here also. QH L over. So one L is here, this is L cube, and one L is here also. So it will be QHL over 12pi. So you can calculate then delta V as theta V into H. So QH square L over 12 pi. Agreed? 2 times, so this will become 6 cycles. No, I have multiplied by h. So yes, it is okay. Not h by 2. Theta v into h I have taken. So that will be our delta. How much will delta c? So it will be 2 times whatever deformation is occurring here. How much is this deformation?
Q to L by 2 Q. Q. L by 2 Q.
L by 2
H by 2 H by 2
over
3 L.
so not L, it will be h over 3 EIC. So how much is that? So 8 into 3, 24 divided by 2, so 12. So QHQ over 12 EIC. I can now write down delta. So delta is QH square L over 12 EIB plus QHQ over 12 EIC. this I can write down as QH square over 12E. If I take outside, it will be L over IV plus H over IV. Okay, so this expression is giving us a linear relationship between Q and delta. Okay, so this is like 1 upon K, flexibility. Okay, inverse of stiffness, or Q is equal to K delta, stiffness into delta. So this is a linear relationship. Till when it will continue? Till when this will continue?
Up to E.
In where?
At the junction.
Junction. At the junction there are 4 members. So which member is going to yield?
Demand to capacity ratio will be
Where the demand to capacity ratio will be maximum. Okay. So you can calculate the demand to capacity ratio of all these members. Let me call it this as 1, this as 2, this as 3, this as 4. So what is the demand at 1? Q into H by 2. Demand at 2?
same. Q into H.
Demand at 3?
Demand at 3. Q into H.
And demand at 4? Are you sure at 2 also it will be QH by 2? Or it will be QH by 2? Check. QH by L into L by 2. So that will also come out to be QH by 2. So the demand at all the 4
Will be
same in this case. Okay. So where you expect the hinge to occur? Demand is same.
At the same time.
So that will depend on capacity.
Capacity.
Where the capacity is lower. Okay. In first semester you have learned strong column weak beam design. So if it is a strong column weak beam design, and what we are doing there, summation MC is greater than 1.4 times summation MV, the capacity. In column was more. Demand is same at the joint. Where 4 members are meeting, you can see that the demand is same, irrespective of the span and the height. L is not coming into picture. So demand is same. So it will depend on capacity. That's why just checking the capacity irrespective of the span of the column, if you check the capacity at the joint, that is enough to ensure whether the beam is going to yield first or the column is going to yield first. So from this you can see that the beam will yield positive. Let us say the yield capacity is MBY. Can you calculate QY? So hinges are forming in the beams here. So the beam will form hinges, and when the hinges are forming in the beam, this moment capacity here is MB. Why? Okay. How much will be value of Q at that time? Can you tell me? Just now you told me that the demand is QH by 2 in all the members, including beams. So QH by 2 or Q by H by 2 this is equal to MBY. So that means QY is so this is what is delta Y? In that condition, you substitute the value of Q here. You will get delta. Substitute Q as QY, you will get the value of delta.
MBY is the capacity of B.
Right.
Total B.
Total beam means what? Capacity means moment capacity of a section. Right. It doesn't depend on the length of the beam. It depends on the section of the beam. So these sections here, these are having yield capacity MBY. Okay. Here we are assumed to be same. It may not be same also. Because this column, this beam is in sagging. This beam is in hogging. Okay. So it may not be same also. Let's assume for the time being the same.
Sir,
Yes.
the objective behind to consider for that is in this form in the beam because we have considered a strong point in beam.
Right.
Okay. What we have to do with that MBY objective
We want to calculate, our objective is, we want to calculate the yield force. The force, the lateral force which is acting on my building, at which my structure is going to yield. Okay. And the structure I have divided into sub-assemblage. So at what lateral force my sub-assemblage is going to yield, that force I can calculate.
Like a section building movement.
Sorry.
Section beam building. The beam section.
I'm interested in yielding of my structure. Now, yielding of structure will depend on the yielding of the component.
Yes.
So, if I have a nice strong column beam, which component is going to yield? Beam. And when will beam yield? When the section of the beam subjected to maximum bending moment is yielding. Where is the maximum moment in a beam of beam? Near the joint.
Yes.
So whatever section you have provided near the joint, when this section is yielding, okay, then the yielding of the structure will take place. Our objective of doing all this is to plot the non-linear relationship between Q and delta. So far we have obtained linear relationship when nothing was yielding, but now the beams have yielded, so the relationship is going to change. once the beam yield, what will happen to delta? Once this yielding has occurred, our structure now will be can it resist any load? If I have this type of structure, can it resist any load?
Yes. Beam is yielded, but column has
Yes.
capacity to resist.
Right. So plot the function. So if it can deform without any load with Q equal to 0, okay, that means it has become a mechanism. If it requires some force to deform, then it can still resist the load. Mechanism has not formed. So you plot the deformed shape and see whether any force is required to cause the deformed shape. So for the time being, let us assume that it has not become a mechanism. So it will require some force. And when it will require some force, then our column is going to deform like this. Okay? What will happen here? There will not be any movement because these are pinned now. There can't be any movement. So beams will remain straight. So there is no moment here. Can this be in equilibrium? How this force is causing the moment on the joint? On the joint, this is causing a moment in this direction. At this joint, this is causing a moment in this direction. But the moment here and here is 0. So can it be in equilibrium? No. Joint will not be in equilibrium. So there should not be any moment at the joint. What does that mean? That means that Q is equal to 0. So it cannot resist any force. Now let's go other way around. I assume that it can deform as a mechanism and see whether that hypothesis is okay or not. So if it is a mechanism, it is going to deform like this. And what will happen to my beams? Is it possible? Or any problem? It's possible. So that means that after formation of the hinges here, my structure has become a mechanism. It can deform without any addition. Okay, so my Q delta curve will become flat. Till when it will continue?
This rotation equal to theta y to theta u, theta y to theta u.
Theta by
Theta u.
theta. So when the plastic rotation capacity of the beam is exhausted, okay, or the beam rotation reaches theta u. Okay. So let us say theta b u is the total ultimate rotation capacity of beam. So how much will be delta under that condition? So delta u will be delta b u plus delta c u. At the ultimate rotation in the beam, how much is the displacement due to bending of the beam and how much is the displacement due to bending of the column when ultimate point in beam is reached. So how much will be delta bu? Can you tell me? Delta bu is the displacement when the beam has reached its ultimate rotation capacity, theta bu. So how much will be delta bu? I have drawn the perpendicular to the column. You can see that the perpendicular to the column is no more tangential to the beam. Why? Because in elastic condition, the rotation of beam and column was same, but now plastic rotation has also. Okay, and this total rotation is theta bu, out of which this was theta by. After that, the beam deformation is not changing. Beam will go on deforming till the yield moment occurs. After that, the beam is not going to deform any further, but still the rotation can occur, because the plastic hinge can continue to rotate. So, in that condition, how much will be delta BU? Theta BU into H. Agreed? So delta BU is theta BU into H. And how much is delta CO? The columns are deforming like this. So this is our delta CU by 2. So you can calculate how much force is acting here.
Sir, to get delta CU, plastic hinge must be found in column also.
Why? When the beam have yielded, it cannot take any more moment. So the moment in the column also cannot increase. So column cannot yield. The beam will go on deforming and beam will break, collapse. Okay. But moment is not going to increase. So if moment is not increasing, how the column will yield? Column cannot yield.
If column is not yielding, then how in column rotation, how it is going from theta y to theta u in column?
We are not talking about delta U of column. We are talking about delta U of structure. And in a structure, even if the beams have yielded, even then the structure has yielded. It's not that for yielding of a structure, every member there has to yield. Okay? In a structure, in a frame, even if the beams have yielded, the structure has yielded. When the beam will fail, the structure will fail, even though columns may be intact.
Yes, sir, but whatever we are calculating delta CU for
Delta CU is not the displacement when the columns have reached ultimate. Delta CU is the displacement due to bending of column when the beams have reached
yielded.
Beams have yielded and they have reached their ultimate location. Okay. So at the ultimate point, beams are reaching. At that point also, column is having some forces.
Yes.
Not the yield forces, less than yield. But some forces are there. Due to that, it is going to deform. So that deformation we have to consider. So it is not the deformation when the column is going to reach the ultimate point. When the beams are reaching the ultimate point, at that time, whatever forces are there in the column, you determine those forces, QU, and then under those forces, you calculate how much columns will deform. Columns are still elastic. So how much will be QU? Yes.
So we are assume that due to some design philosophy, our column both the beams and the column both are getting
We will
saturated.
come. One second. Those cases, we will make life more and more complicated. Don't worry. But let's start with simple. So let's keep our life simple for the time. Can anybody tell me delta CU? How much is QU? when the beams are yielding. Let us say the ultimate moment capacity of beam is MBU. So QU will be simply MBU divided by H. Agree? You agree? Calculate this reaction. Okay, how much is this reaction?
Sir, delta mu by 2 होना चाहिए जी।
कहाँ पर? Where? Here?
Diagram.
Yes, you are right. It is delta mu by 2 and this will also be delta mu by, you are right. So you agree? Q will be MBU by H? No?
Sir,
Then calculate.
Sir, QH by 2 equal to QH by 2. The demand should
QH
be
by 2.
equal to MBU to get QU.
Mhm.
Then from that we will calculate QU.
Okay. So how much you are getting?
QH by 2 Q equal to MBU
2 MBU by H.
GH.
Okay.
Now delta C equal to PLQ.
Then delta C will be how much? Into H by 2 Q over 3 PX
Into 2.
into 2. Good.
So,
Yes.
when the partitions are formed in B,
Right.
then also the column is having some capacity which is very big.
Then also it is having some capacity. Yes. It can take more load.
It can take.
Right.
How is that load transfer? When the beams are.
No. It can take more load doesn't mean it will be subjected to more load. Capacity of the column is more, but that much load is not being applied on the column. That's why it remains elastic. That's why we are using this formula PLQ over 3L. So column is still elastic. It has more capacity to take load, but that much load cannot generate on it because beams have yielded. If you want to apply more load, beam should be also able to take more load, but beams can't take more load. So although columns have some spare capacity, but that capacity we are not utilizing, we can't utilize. In fact, we do not want to utilize. We want our column should remain elastic. Beam should yield. Do you recall why? Why we want that? That column should yield, not beam. Sorry, beam should yield, not column. Why do we want that? Strong column weak beam design. Why? This is strong column weak beam design. That beams are yielding, but columns still have some spare capacity. 40% spare capacity we are giving to the column.
Capacity design.
Yeah, this is capacity design. Why you do that? This is capacity design. This is strong column weak beam design. Okay, but why do we do that?
In earthquake, we want to dissipate energy. In earthquake, we want to dissipate energy to form beams, not form columns.
Why?
If the column gets fails, whole structure will get fail. But
No.
one of
If
the
columns fail, only that story will fail.
no, if the below column will fail, the whole it will fail.
No. The first floor, I have shown you photograph. The first floor will come to the ground floor. That's it. It has happened in Ahmedabad during Yogendra.Earthquake. So I am not talking hypothetically. Rest of the building was intact. Only the cars got crushed. Otherwise, everybody was safe. Avoid brittle failure. How it avoids brittle failure? If you make columns remain elastic and the beams yield, how that avoids brittle failure?
Because beams failure in ledger and ledger is a type of
Columns fail. We do the capacity design of columns also. We ensure that columns also not fail shear. To shear capacity we make more than the flexure capacity. In the beginning of this semester, not beginning, few classes earlier, I have asked you to plot moment curvature curve of the column for different values of P. Do you remember that? What was happening when you plot the moment curvature curve at different values of P? When P is equal to 0, please do that exercise again. So for different values of P, this is our inflection curve for the column. This is P equal to 0. Let us say this is P1, this is P2. So for these three values of P, you plot M versus phi qualitative. P equal to 0, P equal to P1 and P equal to P2. P1 is less than balance failure. P2 is more than balance failure. Okay. Can you plot three curves qualitatively? We did this in one of earlier classes, but I want this should be always clear in your mind. Let us say at P equal to 0, the curve is like the beam. So let us say this is the moment curvature curve at P equal to 0. You plot for P1 and P2. Sorry? You're right? Not worry. Have I forgotten any question so far? No. I will not forget your question. We will not skip any question. But we are preparing background for that question. But at P1 the moment capacity is larger. Yes. Equal to 0. Some of the hour 22. But at P1 the capacity is larger than P equal to 0. You can see there. In fact, P1 is having the maximum moment capacity. Okay, so please continue with this. Plot this curve. Think. I have already done once in class. You need to think about it. Okay. You should never forget this. And remind me about your question in the next class when we will meet. Monday. Monday class I am taking. So Monday 4 to 6 class. Next week I will take. Wednesday there is Senate meeting. So Wednesday's class will be taken with that. So we are exchanging Monday.